Welcome back. In this video, we are going to start with chapter 4 about higher order derivatives or differentials. So there will be 3 sections in this chapter, and the first section will give definitions and some basic examples and properties. But in order not to make a lengthy video, I will split this section into 3 videos. Okay. So let us first start by understanding second order derivatives before we move to higher orders. So consider a map F as usual from an open subset of a normal space into another normal space, and assume that it's Frechet differentiable on its domain. Then the derivative map, is a function from U into the space of linear bounded maps from E to F. Okay, so F and F prime have the same domain, but different target spaces. Okay, so what we said about the differentiability of F, we can apply to F prime. So if F prime is differentiable at the point A of U, we say that F is twice Frechet differentiable at A. Okay, and the derivative of this map, so instead of writing F prime prime of A, we write F double prime of A, and it's a bounded linear map from E into the target space of F prime, which is L of E and F. Okay, so the second derivative is actually a bounded linear map from E into the target space of F. Okay, and we identify this, as you know, with the space of bounded bilinear maps from E times E into F. Okay, so we may write the second derivative F double prime or D square F, and you may find other notation in the literature. Okay, so use the notation that you like. Okay, so for the derivative, F prime of A, as you said, is a bounded linear map from E to F. Therefore, it needs an argument, and that we usually call H. But since the second order derivative is bilinear, it needs 2 arguments. Okay, that we usually denote by H and K. Okay, or H1 and H2. Okay, so if H is an E, F double prime of A in the direction H is a map from E to F. Therefore, it acts on E. So if you take K in E, then the result will be in F. Okay, so this is what you. Okay, so and as you said, we can consider the second derivative as a bilinear map. So instead of writing F double prime at A in the direction H in the direction K, we simply write F double prime of A at HK. So we have 2 independent directions here, H and K. Now, it's not necessary to use this identification, but in some cases it simplifies the writing of some tedious formulas. Okay, so instead of, and especially this will become convenient when we have when we will consider nth order derivatives. So we'll have n arguments, h1, h2, hn. Okay, we'll get back to this later. Okay, so I have 2 points of view for considering F double prime. So either as a linear map into the space of linear maps, or as a bilinear map from E times E into F. Okay. And as usual, if the second derivative of A exists at every point of U, we say that F is twice Frechet differentiable on the whole domain U. And therefore, in this case, we get a map from U into the space of bilinear maps from E times E into F. Okay. So note the difference in the target spaces. So F and F prime and F double prime, when they exist, of course, have a common domain, usually. But the target space of F is capital F. The target space of F prime is L of E and F, and the target space of F double prime is L2 of E and F. Okay. And as you expect, we say that F is of class C2 or twice continuously differentiable if this map is continuous. Okay. Now, we don't need to assume that F is differentiable on U in order to define the notion of second derivative. It's enough that F be differentiable on a small neighborhood V of A included in U. Okay. This is F prime, not F. But in practice, this makes little difference because differentiability, as you know, is a local property. So if F is not differentiable on U, but only differentiable on a smaller neighborhood, you can restrict F to the smaller neighborhood and study F and its successive derivatives inside the smaller neighborhood. Okay. So as usual, let us start by some trivial examples. So in the case of a function from an open set of R into R, if it is twice differentiable at the point A, then by definition F double prime is a linear map from R into the space of linear maps from R to R, and we agreed in chapter 1 to identify this space with R, right? And this space with R. So actually we can consider F double prime as a number, okay? And this is the familiar notion that you studied in calculus. Okay, so what you study in calculus is a particular case of our more general study. Okay, so this identification, so considering F double prime in the case of a map from R to R as a number, amounts to identifying the bilinear map F double prime with its value at 1, 1. Okay, because a bilinear map, as you know, from R times R into R is necessarily a multiple of X times Y. There's no other form, actually. So, as you know, all linear maps from R to R are of the form AX, or constant times X. We saw that in chapter 1. Bilinear maps have a similar form, but you have two variables. Okay, so constant times X and Y. And when we set X equal 1, Y equal 1, because X and Y are in R, then we get B11 equals C. Okay, so this amounts of identifying the bilinear map with its value at 1, 1. Okay. And more generally, if we consider a map from an open subset of R into an arbitrary norm space, then by definition F double prime is a linear map which is automatically bounded, of course, into the space of linear bounded maps from R to F. And since this space is identified with F, then this space is identified with the space of linear maps from R to F. And once again, if you use the same identification over time, we see that this is isometric to F. Okay, so once again, this amounts of identifying the bilinear map with the value at the point 1, 1. Because also in this case, a bilinear map from R times R into a norm space is necessary of the form xy times a constant vector. So I wrote it here xya instead of axy, because usually put scalars in front of vectors. So when we, once again, if we put x equal 1, y equal 1, we get A. Okay. So this is so this means that what you studied in calculus is a particular case of what we are studying now. Okay. But we replace numbers by linear maps or bilinear maps. Okay. Next example, almost trivial, but less trivial than the first one. Okay. If we have an inner product space and we consider the map that associates to each element its norm squared, so the inner product of x by itself. Okay, actually, maybe you proved that f is C1 and you computed its derivative in the exercises, and I added this in the lecture notes. But now, since I didn't do it in the videos, I will now revisit this example. So how to find in a very simple way, without using ghetto derivatives or compositions and so on, we can very easily find the first order Frechet derivative of f. Okay, so let us first find the first order. So this method is very simple. It works in many cases. Okay? So you are not obliged to follow the methodology of finding Gâteau derivatives first. And okay, so we first start by estimating, if possible, the difference, the increment in f. So we compute the difference between f of x plus h and f of x. Okay, so we replace f by its value. And the norm square of x plus h is just the inner product of x plus h by itself. And using the bilinearity, we get xx plus xh plus hx plus hh. So by the rules of the inner product, so we get the norm squared of x plus twice the dot product of x and h plus the square of the norm of h minus this guy. So we simplify by the norm, and we get this very simple quantity, twice the norm of x, the inner product between x and h, plus this term. So you should easily see here that, so you have to look at the linear term in this expression. The linear term is necessarily this guy. And of course, it's bounded in h as a function of h, because in absolute value, by the Cauchy-Schwarz inequality, this is less than the norm of x times the norm of h. So this guy is linear and bounded in h. So this is a very good candidate. It's the only candidate of being the Frechet derivative, first order Frechet derivative. Okay, so when we subtract this linear term, we get an error, which is norm of h squared, which is indeed small o of h, because when we divide by the norm of h, we get norm of h, and this tends to 0. Okay, so actually, it's a big O of h, of norm of h squared. So therefore, we have the differentiability condition at x. X was arbitrary. So this identity, of course, near h equals 0. So this identity means precisely that f is differentiable, is Frechet differentiable at x, and its derivative is given by this linear term. Okay, so this is very, very easy. You don't need Gâteau derivatives, and you don't need any other sophisticated method. So it's really very simple. Okay, and now I'm going to do the same thing with f prime. So I have to take f prime of x plus another increment that I need to call k, because h is, so we have two increments, as you know, h and k. So I evaluate this increment in k. So f prime of x plus k minus f prime of x. But I evaluated at h, you'll see why. So this gives me the derivative at x plus k in the direction h minus the derivative at x in the direction h. And so I replace these derivatives by the value obtained before. So I get twice the dot product. And then by using the linearity with respect to the first variable, I get twice the inner product between k and h. And now you should see that this term here is actually bilinear and bounded in kh. So this will be our second order derivative. Okay, so we can write this in two ways at least. If we want to go exactly to the definition, we let capital L denote the map from E into the space of linear bound maps from E into R. So actually L of k evaluated at h is just this. Okay, so it's a function of two variables actually. And therefore, so I have f prime of x plus k minus f prime of x minus L of k. Everything evaluated at h is 0. So recall that this is a linear operator. Okay, so it is, if it vanishes at every vector h, then it's the 0 operator. Yeah, so this is just Lk, not L. Should have Lk here. So of course it's 0, and here I eliminated the h. Okay, here my increment is k. So the 0 is of course a small o of everything near k equals 0. So this precisely means that the derivative, that f prime is differentiable at x, and its Frechet derivative is given by this operator L. right? So there's a k here. And that's it. So f is twice differentiable at x, and x was arbitrary. And now observe that this L does not depend on x, so it's a constant. So otherwise stated, f double prime is a constant. And therefore of course, differentiable. So actually f is C infinity. Okay. And of course, constant means continuous. So we proved that f is of class C2, and we computed its second order derivative that you can write in two equivalent ways, either as two scalar product of kh, or if you like as, so you can think of L either as a bilinear map of k and h, or as a linear map that takes values in the space of linear maps. Same thing. Okay, so you are free to choose the interpretation that you want. Okay, so I hope that this is clear. And if you want to be more specific, if you want to see between which spaces f double prime of x acts, it acts from E because here U is E because x is arbitrary. And when I apply f double prime to k, I get this partial map. Okay, so this is what I call L of k. L of k itself is a map from E to R. Okay, so this representation may be useful actually. So we can think as f double prime as this map, this complicated map from a norm space into a space of linear maps. This is, by the way, the dual of E. Or simply as just bilinear map from E times B into R. Okay, you choose the interpretation that you like. And finally, observe that since the inner product is symmetric, we can interchange H and K. So otherwise stated, f double prime of x in the direction k in the direction h is the same thing with hk reversed. Or if you think in terms of bilinear terms, f double prime at x evaluated at kh is the same as f double prime of x evaluated at hk. And as you shall see, this is not a coincidence. This is a general theorem that we shall prove in the next video. Okay. But before moving to the proof of this proposition, let us establish a very useful rule for second order differentiation. So I illustrated how to compute second order derivatives in a simple way. But I will give another way because it may be confusing, because here we have two variables, h and k, so it may be confusing, but actually it's not confusing. So if f is differentiable on u, then as we know, f prime of x in the direction h is an element in the target space, capital F. So as x and h vary, we get a function of two variables, x in u and h in e. And I call this function g. Okay. So by definition, g of x and h is this term, capital F, in capital F. And we have to observe that g is by definition linear and bounded in h. Not necessarily linear and bounded in x, but it's necessarily linear and bounded in h, the second variable. Okay. So otherwise stated, I can write this in this form. This is the partial map. Okay. This is the partial map. This is the map as a function of h, fixing the first one. Okay. Now you may check, and I encourage you to write the details. Differentiability of f prime at the point A is equivalent to the partial differentiability of g at A with respect to the first variable. Okay, because here g is a function of two variables, so I have two. Of course, the derivative of g with respect to h is just f prime of x because it's linear, as you know from chapter 1, 2. Okay, so please take a paper and a pen and check what I'm saying. Okay, because it's important and it gives you a practical rule. Okay, so therefore, when we differentiate both sides with respect to x, fixing h, we'll get that the partial derivative of g with respect to s at the point A is exactly f double prime, or if you like, when we estimate this in the direction k, I get f double prime of A at k. Okay, and this precisely means that if we put all the variables together, that the partial derivative of g with respect to x at the point A in the direction k and h is this second order derivative that we can write f double prime of A of k and h. Okay, so what does this mean? This is the practical rule. It means that in the equation g equal f prime of x h, I fix the h, okay, because I have two variables. I fix the h, and I differentiate with respect to x and put x equal a, okay, in the direction k. Okay, now I will illustrate this on a simple example. So let us revisit this inner product example before. We know that the derivative of f at x is in the direction h is just the dot product. So it happens in this case that the derivative is linear in x as well, but this is not always the case. Okay, so what is the derivative of g with respect to x if I fix h? Since g is linear and bounded in x, then its derivative is equal to g. Right? This is by chapter 2. This is the fundamental example. The derivative of a linear map is the linear map itself. Right? Therefore, when I fix h and differentiate in the direction k, I get precisely g, but instead of x, I replace it by k. Okay, and this is just twice the inner product between k and h. Okay, and once again, I get that the second derivative of f at x in the direction kh is just this inner product. Okay, so very, very, very easy. Okay. Next example, a little bit more complicated, but I will use this rule to illustrate another fact, actually, to find a relation between the second order derivative of f, if it exists, and its partial derivative. So here we are considering a map of n variables. Okay, not necessarily real all. So each variable can vary in some norm space, ei. Okay, so we know from chapter 2 that there is a relation linking the total derivative and the partial derivatives. Okay, so f prime of x in the direction of the vector h, which is now an n-tuple, okay, is given by a sort of dot product between the vector of partial derivatives and the increment or the direction h. We know that. Okay, therefore, if I apply the rule, I need to differentiate, I fix h, as we said, and I differentiate both sides with respect to x in the direction. Now I differentiate with respect to the jth variable, not with respect to x. Okay, so I choose an index j, and I differentiate both sides with respect to xj. Okay, so the derivative of this with respect to xj is by definition this guy. Okay, and the derivative of this is the derivative of a sum, finite sum, is the sum of the derivatives. So I can interchange. And now here I'm fixing hi. So the derivative of this is the derivative of this linear map with respect to xj. So it's the derivative of the derivative at the point A in the direction kj. Okay. And as you expect, instead of writing del over del xj of del f over del xi, you simply write del square f over del xj del xi at the point A. And if I equal to j, then we write this as del square f over del xi square. And there are also other notation that are sometimes convenient in other places. We can also write capital Dj, capital Di f of a, or partial j, partial I of f of a. Okay. Okay. Therefore, I just rewrite this, the equation that I obtained by applying the rule. So here I differentiated both sides with respect to xj at the point A in the direction kj. Right? Kj is an ej. And now, of course, if we wish, we could rewrite this term, because now this is really a function of two variables. It's bilinear now, so it's linear in kj and in each I. So this is just a notation, actually. So instead of writing this way, you can write it in this way. But you are not obliged to put it in this way. You can just write it here like this if you prefer. Okay, and now I use the same relation giving the total derivative in terms of the partial derivatives, but this time I apply it to f prime, okay, in the direction k, k1k. Okay? And of course, instead of I use another symbol j in order not to, I have to use a different symbols actually, okay, as also I have to use two different directions, k and h. Okay, so I just need to, so now I apply the vector h1, I apply all, both these two terms are actually linear maps, so they act on vector h1, hn. So when I apply them at h1, hn, I get this. And now, of course, by definition of the sum of functions, this is the sum of this map evaluated at this variable. So this term actually is exactly equal to this term. Okay, so and therefore this is equal to the sum of the sum. So sum over j of sum over I of the mixed partial derivatives at A in the direction kj hi. Okay. Now I can of course interchange the order of the summation because summation addition is commutative. Okay. But you have to be a little bit careful when interchanging the order of derivatives, as we shall see. Okay. So I can write this equation. So this is the relation giving the second derivative, between the second derivative and the partial derivative, the second order partial derivatives. Okay. And I can write this in a matrix form if you like. So I put now inside all these mixed partial derivatives inside one matrix, but it's a matrix of linear operators actually, or bilinear operators. So here it's understood that this operators will be applied to K1, then you have to add the second one applied to K2 and so on. So just the usual inner product. So this gives me the first component, second component, same thing, and last one will be this operator applied to K1 plus second one applied to K2 plus last one applied to Kn. So I get a vector actually of linear maps again, and then I apply it to this vector. Okay, so this is just very convenient. And this matrix is called the Hessian matrix of f at A. Okay, so you can think in this case of a function of n variables, we can think of f double prime essentially as a matrix of mixed partial derivatives. Now, as we already mentioned, f double prime of A is symmetric, so I can interchange the roles of h and k. Therefore, the operators in the diagonal are also symmetric because you are differentiating with respect to the second variable. However, for the other maps, if I is different from j, it doesn't make sense in general to say that the cross partial derivatives are symmetric because each argument lies in a different, maybe in a different space. So ki varies in ei and hj varies in ej. And I didn't assume that ei equal to ej. Okay. So the mixed partial derivative is a bilinear map from ei times ej into f, and the other way around, have to flip the order. Okay. Okay, so this concludes this example. And now, so I will stop here. And in the next video, I'm going to prove this important result about the symmetry of the second order derivative when it exists. Okay, so thank you for attention and see you next time.